In previous lecture, we have seen the structural stiffness matrix, how we have formed using the degrees of freedom activation. So we have discussed that if we have some 100 or 200 number of elements, it will be difficult to activate each individual degrees of freedom. So we should be coming up with some formulation for that. So in this lecture, we are going to see how we can formulate an elemental stiffness matrix which can be used, or which is an universal matrix which can be used for all the elements irrespective of the angle it's making with the horizontal. So for that formulation, here I've taken a element, truss element. This is node I and this is node J. Let's say the length of the element BL, and it is making an angle beta with the horizontal. These are the global x-axis and y-axis. So we will first displace the node I to a prescribed displacement of ui. Once we displace it, this member, the member which we are considering here, will be displaced to this point. So once you resolve the component along the member, we'll get how much the member has displaced, or the final length of the member after displacement. So there will be axial shortening of the member which is equal to u1 cos beta. So before going into the procedure, these are some of the assumptions. Let us consider the cross-sectional area, elastic modulus, and length be the properties of the considered element, which are denoted by i's in the subscript. And we have seen here there will be an axial shortening in the length of the member, and we displace the node I to a prescribed displacement of ui, that is obtained as ui cos beta. So using the stress strain relationship sigma equal to E epsilon, we can obtain the epsilon as delta L by L, which is the change in length is ui cos beta by L. This is the strain, and E is elastic modulus. Stress, we can write it as the force developed in the member by the cross-section area of the member. So using this formulation, we can obtain the final force that will be developed in the member as EA ui cos beta by L. So this is the force that is acted along the member, but we are considering here the global axis. So in the local coordinate system, we will having a force of EA ui cos beta by L. So we need to resolve it along x-axis and y-axis. So the x component will be f cos beta. So this is the force, right? Once you resolve it, you will get f cos beta. In y-axis, it will be f sin beta. So we'll be denoting the x direction force as p and y direction force as q. So this is the f, as I have explained in the previous slide. So once you resolve it, you will get the pi and qi, and here we will get pj in the x and qj in the y. So f cos beta will be having a cos square beta term, and f sin beta will have cos beta sin beta term. So from here on, instead of writing cos beta and sin beta, we will be denoting it in a simple form, cos beta as c and sin beta as s. This will be the convention which we will be following in the further course also. So this is the angle beta. We'll be coming to this point again, like how we are considering the angle beta and what should be where should we start the nodes with. Means I can consider here also, right, the angle beta, what the horizontal is making with j, why I am considering it pi here. So these are some things we need to remember before formulating it. So I'll be going through that in short time. So we have seen what are the forces that are obtained and displacement ui is applied at the node I. So this will be the first vector of the final structure stiffness matrix. So similarly, if you activate the other degrees of freedom in the same element, we have displaced u1, ui I say. So we can displace vi, uj and vj. the other 3 degrees of freedom also. So this will be for ui, this will be for vi, uj and vj. So this is how the overall stiffness matrix for that element will be obtained. Here this is ai ei by li. So this will be the elemental stiffness matrix. This I think you need to note it down. This will be useful for our further calculations also. We'll be doing some examples where we will be using this elemental stiffness matrix. So c square and cs minus c square minus cs, cs s square minus cs minus s square. Here also you can see the properties which we have defined previously for the stiffness matrix. The diagonals are all positive, c square, s square, c square. As it is square, it will be always greater than or equal to zeros. So even the zero is omitted in the elemental or structural stiffness case, so we won't be having any zeros. But there will be a special case I will be dealing, so where you can see we'll be having the zeros here. So mostly it will be a positive number here, and the matrix is symmetric matrix. I hope you might have taken down the stiffness matrix. So yeah, so the final equilibrium equations will be, this part is k, this is d, and this is r. These are the forces and degrees of freedom and the stiffness matrix. So which I mentioned the special case when we consider beta as 0. What happens when beta is 0? When beta is 0, it will be in a horizontal member with node I here and node j here. In that case, this is how the stiffness matrix will look like. So when beta is 0, sin beta will be equal to 0, right? Wherever you see the s terms, all those terms will become as 0, and wherever you see the cos terms, you will be having the 1 value there. So minus c square will become minus 1. Wherever s is there, all the values will become 0. So if you observe the k matrix here, the second column and the fourth column, second row and the fourth row are zeros. But we discussed that in a stiffness matrix, along the diagonals it can never be 0, but we can see the zeros here. What might be the reason? Like if you go to the figure again, so when beta is 0, we will be having a straight member, right? So what will be the degrees of freedom of this member? It is a straight member, it is not an inclined member. So we don't need x comma y coordinates if it is a straight member. Just need the direction in the x. So it is just xi. No yi terms will be there. So there won't be any displacement in y direction. So we won't be having vi and vj. That makes the matrix as ae by l 1 minus 1 minus 1 1. Just 2 by 2 matrix of k and 2 by 1 vector, degrees of freedom vector. Even the force vector will be a 2 by 1 vector. So when beta equal to 0, it represents the straight element with only 2 degrees of freedom. So we won't be considering these zeros. I mean, we won't be having these degrees of freedom, because of which we will eliminate these rows and columns with zeros. So this is a special case. Even we can take the other special case also, where beta is equal to 90. It will be the same, except that in case of c, I mean cos beta will be equal to 0 and sin beta will be equal to 1. That's the only change, and the degrees of freedom change will also be there. So we have obtained for a single element, right? But we need the stiffness for the whole structure. That is the aim of the problem, right? We need to find the stiffness of the whole structure. So we can do the assembly of individual elemental stiffness matrices to obtain the final structural stiffness matrix. So we will go to the same example which I have discussed even in our previous class. So I explained previously the boundary conditions and the loadings and all. So before going through the whole procedure for the example, so these are the two things we need to make a note down. We need to select two nodal points, naming it as I and j. It depends on your choice. You can take I as 2 and j as 1. Here we are considering element 1, right? So I am taking I as 2 and j as 3. Even you can take I as 3 and j as 2. first you need to fix the I and j node numbers. Which node number you want to take it as I, and which node number you want to take it as j. Once you fix the node numbers, then we need to decide the angle. So whatever may be the node I you are going to take, you should find the angle that node I is making with respect to the horizontal reference line, and the angle should be measured in the anti-clockwise direction. So make a note of these two things also. These are the two main steps. Most of the mistakes will be done in these steps while formulating the stiffness matrix for an individual element, where your whole problem might go wrong if you do a mistake in these two steps. So these are the two main steps. Select the nodes I and j initially, then you need to find the angle with which the horizontal is making with respect to the node I in the anti-clockwise direction. Even the direction is very important. We'll see that when we see the inclined member 2. We found out the elemental stiffness matrix of member 2, it will be more clear for you, but better you remember these 2 points. So starting with member 1, I have considered this node as I and this node as j. So the horizontal is making an angle beta 90 degrees. So once you place C0 and S1, so you can find the stiffness matrix. This will be the stiffness matrix, and the corresponding degrees of freedom will be U2 V2, U3 V3, and the corresponding forces also. So similarly, as I mentioned previously, when we have a horizontal member or vertical member, we will have only 2 degrees of freedom. So that is what this zeros means in this stiffness matrix. So now we got the elemental stiffness matrix for member 1. Now we will go to the elemental stiffness matrix of member 2. So this is an inclined member, right? This is the node which I am taking as I, this is the node which I am taking as j. So when you draw an horizontal, you need to find the angle in anti-clockwise direction. So with the horizontal, the member at node I in the anti-clockwise. So using tan theta equal to 4 by 3, this is the theta. So beta will be 180 degrees minus theta. That comes out to be 126.9 degrees. You can check it in your calculator if you have the calculator with you right now. So beta will be 126.9 degrees. So corresponding cos beta and sin betas will be evaluated, and using the same formulation which we have derived here, using these formulations, we will write the final equilibrium equations. Similarly, if we consider member 3, this is the horizontal and this is I. In the anti-clockwise direction, the angle will be 180 degrees. Similarly, again we will find out the equilibrium equations, k, degrees of freedom, and the loads. And here also it is a horizontal member, so we will be having 2 columns of zeros. So now we know the individual stiffnesses of individual elements. Using this formulation we obtained it, but we need the structural stiffness matrix, right? Not the individual elements. The final form should be consisting of all the degrees of freedom with u1, v1, u2, v2, u3, v3. All degrees of freedom vector should be there, and all the load vector, the whole load vector should be there with the 6 by 6 stiffness matrix. As the degrees of freedom are 6, if we recall the properties of a stiffness matrix, it should be n by n. So it should be a 6 by 6 matrix. So, but why for this assembly, in this assembly, what we are going to do is, we need to assemble only the unknown degrees of freedom. Assemble the stiffnesses with unknown degrees of freedom which we need to evaluate. If we go back to the example, you know V2, U2 and U3. These 3 degrees of freedom are known. So the unknown degrees of freedom are U1, V1 and V3. These are the 3 degrees of freedom which we need to evaluate. This is our problem. So while assembling also, we will look into these 3 degrees of freedom only. So you can see here I have written A2 E2 by L2, A3 E3 by L3. So the member length and the areas might be different in some particular problems or some particular structure. The areas and lengths might be different. So for simplicity, I am considering all the members are of equal length L and area of A. So that's why I am writing it as AE by L. So now coming to the assembly, of the elements. If you remember, I have mentioned for any elemental stiffness, the first row corresponds to the first degrees of freedom. So u1 is our target, right? So first we will consider u1. This is u1. So this vector or this column should correspond to u1. This corresponds to u1, and if you consider the columns, this first column will correspond to u1, this column will correspond to v1, this corresponds to v3. So we need to find the first element where the combination of u1 should be there. Combination of u1. If you consider here, this is a column of u1, right? And this is a row of u1. So 0.36 is an element which corresponds to u1 comma u1. So in member 3, this is u1, this row is corresponds to u1 and this column is corresponds to u1. So this element is u1 comma u1. But if you see in member 1, there is no u1 degrees of freedom here, so we no need to look into the member 1 stiffness matrix. So in member 2 and member 3 we have the u1 degrees of freedom. So one is from one stiffness matrix we got 1, from the other stiffness matrix we got 0.6. So we need to add those two. 1 plus 0.36 will give 1.36. So the second we need, this is u1, but this corresponds to v1, right? So we need u1 comma v1. Let's find out. This is u1 and this is v1. So minus 0.48. This is u1 and this is v1. So 0 minus 0.48. We are not having any u1 or v1 terms here. So let's omit number 1. So 0 minus 0.48 will give minus 0.48. Similarly, the third is, if you consider the column, it is u1, the row is v3. Let's see where are u1 and v3. This is u1, we have v3 here. So u1 v3 is 0.48. u1, we have the u1 here, but there is no v3. So u1 comma v3 term is not here. Even here also we don't have u1, so no need to go through it at all. So we have only 0.48 in second member's elemental stiffness matrix. So that is 0.48. So that is how we have obtained the first column. This is for structural stiffness matrix, which contains only the unknown degrees of freedom. You can consider the other degrees of freedom also, the u2, v2 and u3 also. The similar kind of exercise you need to do for obtaining the whole 6x6 stiffness matrix. But as the degrees of freedom which we need to evaluate is just u1, v1 and v3, I have omitted the other degrees of freedom. As the other degrees of freedom are zeros, we can eliminate the rows and columns, which will finally land up with this 3x3 matrix. That is the reason why consider only 3 degrees of freedom. So coming to the second column now. See what happens in the second column. This column is corresponds to u1, right? The second column will corresponds to v1. So and the first row will be u1. So column comma row v1 comma u1. Let's see where we have the column v1. We have the column v1 here and u1. Column v1 and u1 minus 0.48. Column v1. This is column v1 and this is u1. 0 minus 0.48. So 0 minus 0.48 minus 0.48. And next we have v1. This is v1 and this row corresponds to v1, so 0.64, and here also we have 0. So similarly we will evaluate the other columns. In this way we can obtain the final structural stiffness matrix, which includes the unknown degrees of freedom. We can't do this always, like obtaining only for unknown degrees of freedom. Here it is possible because of the boundary conditions. The values of v3 is 0, u2 is 0, v2 is 0. That is the reason why we are able to omit the other degrees of freedom. If those are non-zeros, we need to write the whole stiffness matrix. I think we are going to see one more example where we have non-zero degrees of freedom and we need to evaluate the stiffness matrix. So maybe there we can go through the example. In that example we will see that. So remember this part here, the values are 0, the known degrees of freedom are 0, that's why we are considering only the unknown degrees of freedom. And this is the main thing which you need to remember. This is the column which represents u1 and this is the rows which represents the different degrees of freedom. Using this combination we will find the overall structural stiffness matrix, and these are the loads corresponds to u1, v1 and v3. u1 we don't have any load, v1 it is in negative y-axis, so minus p, and v3 I don't have any load, so that is 0, minus p and 0. So this completes the formulation of individual elemental stiffness matrix and assembly of elements. Now we will see how the reaction forces can be obtained and how we will evaluate the stresses using the displacements, what are the methods available, and some other topics also. So these are the topics which I will be covering. So different methods for evaluating these, and if we have till now we have seen the support conditions with some proper simply support or roller. So if the supports are inclined, how we are going to tackle the problems? For that we need how the stiffness matrix will be varied if there is transformation in the coordinates. So the second part will be based on that. I will try to cover this in today itself, but let's see whether it will get postponed to the next lecture or not. In last we will see how if there is a symmetry in the plane truss, how we are going to deal the problems and how to identify the symmetry in the plane truss. That will complete our finite element formulation for plane trusses. So starting with the methods, so these are the 4 different methods for obtaining the degrees of freedom or the unknown forces. By using Kramer's method we can obtain, using the formulation we know kd equal to r. So once you pre-multiply k inverse on both the left hand side and right hand side, we will get the degrees of freedom equal to k inverse into r. That is what I meant by the Kramer's method. So the other is the Gauss elimination method, which you might have practiced in your +1 or +2. So where we will do some row or column operations for eliminating then individual unknown quantities. So these two are not much used for solving, so these we will be focusing more on these 2 methods in this course. So let us see what we meant by reduction or elimination method. So in elimination method, in the previous example which we have solved, we have eliminated both the rows and columns. We have considered only the unknown degrees of freedom. That is the case when we have the prescribed degrees of freedom are zeros. There we have a simply support and a roller support, where we know the degrees of freedom of u2, v2 and u3 are zeros. So that is why we have eliminated both rows and columns, that particular related to the degrees of freedoms, rows and columns. So we will go to the reduction method if we have non-zero degrees of freedoms. So the formulation is similar to what we have discussed might be in previous class. We will be having known quantities and we have unknown quantities, and by expanding this form we will get 2 individual equations. Then we need to subject du from the equation 1. This will be the unknown part. So let's see how we are going to proceed in the reduction method. We know how we will do in the elimination method. So now let us focus on the reduction method. So the same problem I have taken. So I will explain why the springs are being replaced with the simply supported boundary condition and the roller part. So in the example we are considering the u2 value as 0.5 and v2 as 0 and u3 as minus 0.4. The other loadings and all the angles, all other things are remained same. So this is the stiffness matrix which we have obtained previously also. So I have replicated the same stiffness matrix. So what happens here is we have the non-zero degrees of freedom here. These are the unknown reaction forces. So we will remove the rows that are corresponding to the unknown reaction forces or unknown forces. So we will remove the rows. So once we remove the rows, we will left with only first, second and the last row. These are the three rows which will be left, and these are all the degrees of freedoms will be there. And once we remove this part, we will be left with 0, minus p and 0. So u1, v1, v3 will be the unknown degrees of freedom, and 0, 0.5, 0 and minus 0.4 will be the known values, and these are the known forces. So now we can go back to this equation where we need to find the unknown degrees of freedom when we know the known reactions and known degrees of freedom. Using this formulation, we can obtain the unknown degrees of freedom u1, v1 and v3 using the equation 3. This is the equation 3. Using this formulation, we can obtain u1, v1 and v3. Even to get the v3 here, what we need to do is we need to replace this column. This is the last column, right, which corresponds to v3. This should be coming at 3. So this part should be replaced here. So this will be moved aside, and after minus 0.48 K2 we will get 0.48 K2, 0.64 K2. Beside this we will get minus 0.462, 64 K2. So similarly, once we have to replace this column in the third column, then we can obtain u1, v1, v3 in a line and 0.5, 0.0, minus 0.4 in a line. Then we can go to the formulation and we will get the unknowns. Then we will replace back here to obtain the unknown forces also. This is what we will do in the reduction method. So mostly while solving the problems in an exam, we will use the reduction method or elimination method in journal. Let us see what we are going to do in a penalty method, what difference we are going to make here. So in penalty method, we will add an additional stiffness Ks, which is represented as Ks, which is also known as a penalty number, to the stiffness coefficients of individual coefficients of the stiffness matrix. This is stiffness matrix. For some of the elements, we are going to add the additional penalty number Ks. Where we need to add is wherever we have a prescribed displacement. Here, if you consider the example, we have prescribed displacement for u2, v2 and u3. Even it is a 0, then also we need to add the springs. So at u2 we have added the spring, at v2 also we have added a spring, at u3 also we have added a spring. So these are the springs and the coefficients are Ks. So the stiffness matrix will be the same. There won't be any change in the stiffness matrix. We'll use the C square Cs terms which we have used previously. The same things we are going to use, and we find the final structural stiffness matrix using the combinations of u1 or u1 v1, the combination which you have seen in the previous module where we have seen one example. In the similar way, we will obtain the final structural stiffness matrix. Then in addition, we need to add Ks terms wherever the displacement is prescribed. So here this part is prescribed, right? So u3 term. So only in the diagonals we are going to get this Ks terms. Always we are going to get the Ks terms only in the diagonals. So wherever the support is there corresponding to that part, we need to add Ks. This is 5, 5. So at 5, 5 we are going to add Ks term. This is 3, 3 and 4, 4 parts. So at 3, 3 and 4, 4 of the K matrix, we are going to add the Ks term. So we can choose any penalty number of our choice, but if you choose a large number in evaluating K inverse, we might face some problems. So it's better to use the Ks as the maximum of Ks is into 10 power 4. This should be the Ks term which is better to use always while solving a problem. Once you find the maximum of these Ks values, after you substitute K2, K3 terms, what will be the maximum value, you consider that value into 10 power 4. That part will be your Ks. Use that Ks value for evaluating the final structural stiffness matrix. So this is what change you will find in penalty method in the stiffness part. Now let's go what will be the change we are going to see in the force part. So 0 minus P and 0 we know, and these are the unknown forces, right? As we have added a spring here, we don't have a support reaction now. Now we have a spring force. What will be the spring force? Ks into displacement. So Ks into V2. Here Ks into U2. Here Ks into U3. You know the displacements, right? U2, V2 and U3 you know. And we know the Ks parts Ks also. So we know the R vector. The whole R vector we know. The K matrix also we know. Now we can use the Cramer's rule and find the degrees of freedom. Degrees of freedom will be K inverse into R. That gives the degrees of freedom. And once you know the degrees of freedom, you can substitute U2, V2 and U3 to obtain the reaction forces that will be developed at the supports. This is how the penalty method works. So these are the two main methods. One is reduction or elimination method. The elimination method we will use only when the degrees of freedoms are 0. Reduction we will use when we have unknown degrees of freedom. Most possibly or mostly we will use the reduction method than the penalty method. If you are doing some coding for finite elements, then it's of your choice whether to go with the penalty method or the reduction method. But while solving the problems in the examination, it's better to use the reduction method. Now let us see some numerical example on both this reduction method and the penalty method. So this is a bar, unidirectional bar. It will be having a single degrees of freedom. If you recall the definition of degrees of freedom, you can identify that we will be having only a single degrees of freedom here. So two bars are there. One is of length 300, the other is of length 400. These two are connected with some kind of joint, and at the joint we are applying a load P. So these represents the node numbers. 1, 2, 3 are the node numbers, and these are the element numbers. 1 and 2 are the element numbers, and it is simply supported or fixed here. So there won't be it won't allow any displacements in these directions. So using this same displacement method, degrees of freedom method, or by using the same C square Cs formulation which you have formulated previously using the same terms, we can obtain the stiffness matrix. This will be AE by L, A1 E1 by L1. I have told you previously, right? The areas and lengths might be different in some cases. We can't take AE by L as same for all the stiffnesses. You need to be careful while calculating the stiffness matrix because the AE by L terms will be different for different members. So here you can see one of the examples where the different members have different AE by L ratios, which changes the whole stiffness matrix. This part will be same, but the AE by L ratio will change the whole stiffness matrix part. So here the degrees of freedom will be U1 and U2. For the second part, it is U2 and U3. So we have obtained the stiffness and the corresponding degrees of freedom. Now you can use the same U1 comma U1 and U2 comma U2, that part which I have explained previously. So which is the common node here? 2 is the common node, right? So only 2 will be having a combination of coefficients in the structural stiffness matrix. So this part only will have the combination. The other terms will be single terms because the node 1 is not a common part of 2, right? So node with respect to 1 we won't be having any combination, but 2 is being shared with the 2 elements. So only the second part will be having a combination. Sorry. So the second part will be having a combination. So the second part, if you consider 1 plus not 1 plus 1, it will be 0.56 into 1 plus 0.3 into 1. This is u2, right? u2 comma u2. This is u2 comma u2 term. So here we will be getting 0.86. If we consider this part, this one is u1 comma u1, right? So you can see here, this is u1 comma u1. There is no u1 terms here, or there is no u3 terms here. So if there is something on u1, that will be taken from the elemental stiffness matrix of member 1. So we will obtain the final structural stiffness matrix K, and we know the degrees of freedom, right? For 1 and 3, it is not allowed to move in that direction. So u1 will be 0 and u3 will be 0. So using Ku equal to F, the force vector, we don't know at P1 and P3, these loads are unknowns, but this load is known. So we have given the load here. So Ku equal to F. By using the elimination method, as the displacements are zeros, we can use the elimination method. We can eliminate both the columns and rows, and we will be left with, if we remove the first and third row and first and third rows and first and third columns, we will be left only with 0.86. So 0.86 times u2 will be equal to 200 kilonewtons. That gives the u2 as 0.23 mm. This is how the elimination method works. I haven't given any example for reduction method, but this is one of the example for elimination method, where when the displacements are 0, we will eliminate the rows and columns corresponding to that degrees of freedom in the structural stiffness matrix. So you need to practice this structural stiffness matrix, how we are going to form the structural stiffness from elemental stiffness matrix. So then only you will understand how we are able to write the structural stiffness matrix from individual elemental stiffnesses. Now we have done with the example of elimination method. Now going to the penalty method. So in penalty method, as I mentioned, we need to choose a Ks, right? That will be the maximum of Ks into 10 power 4. If you see the Ks part, stiffness part, it will be the same. Whatever may be the method, the stiffness won't be changing, right? So 0.86 times 10 power 6. So the Ks should be 0.86 times 10 power 10. I think I made a mistake here. While you take down the notes, you write it as 10 power 10. While sharing the PPT, I may change this to 10 power 10. So understand, right? K, maximum K here is 0.86. This one is 0.56. One term we have 0.3. The term will be 0.86. If you have positive and negative values, take a determinant of the value, modulus value. I mean, take the modulus value, and modulus of K is a max into 10 power 4. So it will be 0.86 times 10 power 10. As I mentioned previously, when there is a prescribed boundary condition, we need to replace it with the stiffness, spring stiffness Ks. So as these two are the degrees of freedom which we are known, so we have replaced it with Ks. And one more thing, you remember I have told you that we will add only in the diagonal terms. So see here, in the diagonal is 1, and this is 1, right? Node number 1. This is node number 3. So at 1 and 3 positions, we will going to add the Ks values to the original stiffness matrix. Please change this Ks term also. Ks is 10 power 10. I might forget while sharing the PPT, but you need to take care of this part. The Ks part should be into 10 power 4. That is including this 10 power 6. So that is the Ks value which we need to substitute here. So while calculating the force, as we have removed the supports here, what will be the force? Ks times displacement. What are the displacement there? We have fixed it there. So the displacement is 0. So it is Ks times 0. The load is here also, it is Ks times 0, and we know the load P is given as 200 kilonewton. So now we have Ku equal to F, equilibrium equations, and we know the K, we know the F. So now we can evaluate the u vector. So ku equal to f, from u equal to k inverse f, once we evaluate the u vector, this is how we will be getting u1 as 15.14 into 10 power minus 6, u3 as 8 point something into 10 power minus 6, u2 as 0.232. So the u2 value is same by using both the methods, but u3 is 0 there. We know exactly it is 0 there, but when you compare this displacement to this part, it will be approximately 0. So this is how we are going to do in penalty method. So now we have obtained the displacements, right? So we know the displacements and we know the forces also. So but while calculating the reaction forces, what we are going to do is we need to update this u value with this value. While solving, we can use the ks into 0, but once we get the u1 values, we need to use this updated u1 value here for finding the reaction forces. Please take a note of it. Here, while solving, we will use the prescribed displacement as 0 as it is fixed there, but once we evaluate the displacement, we are going to use the same displacement values for evaluating the reactions. Otherwise it doesn't make sense, right? When we take the reaction force as 0, how can we take the force as 0? We call it as a penalty method because we are making it as 0, so we are adding some penalty in the stiffness part. That is why we call it as a penalty method. So this is how the reaction forces will be evaluated in penalty method. So now we have seen different methods how the displacements and reaction forces can be evaluated. So once we know the displacements, we can also evaluate the stresses that will be generated in the member. Let us see how the stresses will be generated. Using same, if stress is directly proportional to strain, sigma will be equated as E times epsilon. Epsilon will represent the change in length by original length. If you consider a element of a truss, this is node I and this is node J. This is VI, UI, Vj and Uj. This angle, let's say it is making an angle beta. So this is the displacement that has occurred already in the member, Uj and Ui. So once you resolve along the member, this is U1 cos beta and Uj cos beta. So what's the net change? Uj minus Ui cos beta. Similarly, resolve the y components also. Vj cos beta, Vj sin beta and Vi sin beta. Sorry, you need to change this part also. I think this is not cos, this is sin. Vi sin beta and Vj sin beta. So the net displacement is Vj minus Vi sin beta. That is the change in length. So we are representing the change in length in some vector forms. This final, if you evaluate this part, the final expression will be the same. Just for as we are using the matrices and vectors, I have denoted in this form. So we know the delta L part. So how we are going to find the stress? Stress is equal to E by L into delta L. So E by L will be multiplied to each of the elements here. So EC by L, ES by L, EC by L and ES by L. These are the displacements. So we know how to evaluate the displacements for an element. Once we get the structure with the loads, we can find the displacements, right, in each of the degrees of freedom directions. So once we get the degrees of freedoms, we can multiply this part to this, but this C might change for different elements. Please take care of it when the length might change. So that is how the stresses in an individual element can be obtained. If the stress part is positive, then we call the member is in, then we can say the member is in tension, and when the stress is negative in the member, then we can say the member is in compression. The member is in compression. So this is how we are going to calculate the stresses and displacements and reactions using different methods. So we have seen the stresses, how we are going to calculate if it is a mechanical force. If there is some mechanical forces that are being applied on the member, then we know this is the procedure. But what happens if there is a temperature change? like in some temperature increment in the temperature has been applied to the structure, so we need to find what are the stresses that will be developed in the member. So we might be using in some industrial area where we deal with high temperature substances. So in that case, even the structure will be subjected to temperature changes, right? So in that case, even we need to consider the temperature changes also. So in the next class, we will see how the temperature change will result in the stresses in the member, and how we are going to include the temperature change part for getting the final stresses.